All right, this is the video lesson for covalent bonding and molecular geometry. So what we're going to learn how to do in this discussion is draw Lewis dot structures for covalent molecules that share electrons, and then use that to determine their shapes. All right, so how do we show the bonding of covalent molecules? So we're going to use Lewis structures. Now you might remember in 3.1 we showed how ionic compounds can form from electrons being transferred from metal to nonmetal. Here, we're going to show that they're sharing electrons rather than transferring. Just as before, dots represent electrons. Now, a bond is formed between atoms when they share two electrons. So we can represent a bond using a line. So let me show you what I mean by that. So if we were going to show a bond between carbon and oxygen, we could either draw a line like this, or we could show two electrons in between them. Those are basically the exact same thing, okay? It's just two different ways of showing the same thing. All right, so every atom is trying to share electrons to get access to 8 electrons so that they can be like the noble gases, okay? We call this the Octet Rule. Now, there are a few exceptions. The most notable exception is hydrogen, which only needs 2 electrons, and boron is another exception, only needs 6. Hydrogen only needs 2 electrons because its nearest noble gas is helium, which only has 2 electrons. All right, so how do we draw these Lewis dot structures? We're going to follow a series of steps, and rather than going through these steps and just reading them, I'm going to show you how we would apply these steps to water. Okay, so we're going to draw the Lewis dot structure for water using the steps that are on your guided notes. So our very first step, and it's really important, is to count the total number of valence electrons for the molecule. So in water, we have 2 hydrogen atoms and 1 oxygen. So we're going to look at our periodic table and say, okay, hydrogen is in group 1, so it has 1 valence electron. So I have 2 hydrogens, each of which have 1 valence electron, and I have oxygen, it's in group 16, so it has 6. All right, so that means I have a total of 8 valence electrons that I can use. Now, I can't use any more than that or any fewer. That's what I have, that's all I can use. My next step is to arrange the atoms spatially, so I have to select the central atom. Now, a couple rules about that. Hydrogen can never be a central atom because it can only make 1 bond. And carbon will always be a central atom. Beyond that, if you have to pick, the less electronegative atom goes in the center. Here, it's really not an issue because hydrogen can't be a central atom, so I know it must be oxygen. Okay? So I'm going to put the hydrogens on either side of the oxygen. Now, there's multiple different ways that you can approach this. I like to start with a single bond between atoms. I know that they're bonded, so I know they must share at least 2 electrons. All right, so I have 2 electrons shared between hydrogen and oxygen here, and 2 electrons shared here. So I've used 4 of my 8 electrons, which means since I started with 8 and I've used 4, I have 4 remaining. Now, if the outer atoms need more electrons, I typically distribute the electrons to those atoms first. In this case, they don't. So oxygen needs 4 more electrons in order to be stable. So I would put what we call lone pairs on the oxygen atom. So this is a lone pair, and that just means that these electrons are not being shared. Only oxygen has access to those electrons. All right, so then I want to double check a couple of things. I want to make sure that I used 8 electrons, no more, no less. And I want to make sure that every atom has access to 8, except hydrogen, which needs 2, and boron, which needs 6. All right, so oxygen has 1, 2, 3, 4, 5, 6, 7, 8. So oxygen is good. Hydrogen has access to 2, which is all it needs, and this hydrogen has access to 2. So this is a correct Lewis structure for water. So let's go back and go through those steps and then apply them to a couple other molecules. So first we counted the number of valence electrons. Next, we arranged the atoms spatially so that the least electronegative element was in the center. Carbon is always in the center, hydrogen never is. We connected the atoms with single bonds. We distributed the remaining electrons outside if needed first, and then on the central atom. We're checking to make sure that all our atoms are satisfied. Now, if we don't have enough electrons to satisfy every atom, that's when we would share more electrons in double or triple bonds. And finally, when we're done, we want to count and make sure we use the correct number of electrons. All right, so we just did water. Let's do ammonia, NH3, and carbon dioxide so that we can just see a couple other examples. All right, so let's try ammonia. So first step always is to count the valence electrons. So nitrogen has 5, each hydrogen has 1. So again, I have a total of 8 valence electrons. Now, just so you know, it's not always going to be 8. The first 2 happen to be, but that's certainly not always going to be the case. All right, so my central atom here has to be nitrogen. So I'm going to put the hydrogens on other sides. And I'm going to start with single bonds in between the atoms. Okay, so now I've connected nitrogen to the 3 hydrogens via single bonds. So I've used 2, 4, 6 electrons. Because remember, each bond consists of 2 electrons. So that means I have 2 electrons remaining. Now all of my hydrogen atoms are already satisfied because hydrogen only needs 2 electrons. So I'm going to put my remaining 2 electrons on nitrogen. So let's check to make sure we use 8 electrons. 2, 4, 6, 8. Perfect. And let's make sure every atom is satisfied. Each hydrogen has access to 2, and nitrogen has access to 2, 4, 6, 7, 8. Okay. Next, we're going to look at carbon dioxide, which is just a little bit more complicated than these first 2 examples. I'm going to erase the one for water. All right, so carbon dioxide, CO2. All right, so first I'm going to count my valence electrons. Now carbon has 4, and each oxygen has 6. So I have a total of 16 electrons. All right, now my central atom, I know that carbon's always the central atom, but also carbon is less electronegative. So carbon's going to go in the middle, and I have oxygens on either side. All right, so I'm going to start with single bonds. So I've used 4 electrons, so I have 12 remaining. Now I'm going to go around and add electrons to the oxygen to satisfy the octet rule. So I've used 2, 4, 6, 8, 10. That oxygen satisfied. 12, 14, 16. Okay, so now I've used all 16 electrons. This oxygen is satisfied and this oxygen is satisfied, but carbon is not. Because carbon currently only has access to 4 electrons, and it needs to have access to 8 to have a stable noble gas configuration. So what that means is that we're going to have to try something different. Now, I could say, all right, well, I can't add any more electrons, so I can't just add extra electrons to carbon. I could take these electrons on oxygen and give them to carbon instead. But that creates a new problem because now carbon is satisfied, but oxygen is not. So rather than doing that, my solution when I don't have enough electrons to satisfy every atom is to use double bonds. So instead of sharing 2 electrons between carbon and oxygen, they're going to share 4 electrons. 2, 4, 6, 8 around the first oxygen, 2, 4, 6, 8 around carbon, and 2, 4, 6, 8 around the second oxygen. So you'll know you need to use double or triple bonds when you really have no other choice but to use double or triple bonds to satisfy every atom. All right, so we've done the first 3. I want you to pause for a moment and try the next 3 on your own paper, on your guided notes, and then you can press play to see the answers. All right, so here are all the structures. Now, one thing that I want to draw your attention to with sulfur dioxide is that it is possible to have a double bond to one atom and a single bond to another atom. Sometimes it happens, sometimes it doesn't, but it's totally entirely possible. Now, this is one of those things that you do need to practice to get good at it. Some people get it right away. Other people take a little longer. There's nothing wrong with either, but just keep practicing until you get it. And remember to count the valence electrons first. That's super, super important. All right, so we're going to talk about how these Lewis dot structures allow us to figure out the shapes of covalent molecules. So we're going to use something called VSEPR or VSEPR theory, and that is an acronym that stands for valence shell electron pair repulsion. So let's think about what that means. That means that valence electrons repel each other. That makes sense, right? We know electrons have negative charges. Things with like charges repel each other. So all of what we call the areas of electron density, so either bonds or lone pair electrons around a central atom, will arrange themselves so that they're as far apart from each other as possible. So basically, electrons repel each other and force the molecule to assume certain shapes. Now, I'm going to go through this shapes chart, and while I do that, I'm going to bring up the simulation that we saw in class so that you can refer back to what the shapes really look like, because just seeing the name isn't incredibly helpful. All right, so when we try to figure out the shape, we have to consider two things. We have to consider the number of bonded atoms around the central atom and the number of lone pairs on the central atom. So when I have two bonded atoms and no lone pairs, the shape looks something like this. So let's take CO2 as an example. So there's two double bonded atoms and no lone pairs. So you notice that's a line, so we call it linear. And that simulation is really nice because you can just click the box and it tells you the molecule geometry, and you can spin it around and it's kind of fun. All right, so if there are two bonded groups and no lone pairs, it's linear. Now, let's say that I have two bonded atoms, but I have one or two lone pairs. Well, then I have a different shape called bent. So let's take a look at what a bent molecule looks like. All right, so I'm going to remove these, and I'm going to use water as an example. So this has two bonded groups and two lone pairs, and so you see that the lone pairs push the bonded atoms into this bent configuration. So if there are no lone pairs, it would be linear, but when I add the lone pairs, they repel the bonded electrons. So whether there's one lone pair or two lone pairs, either way, it's still bent. The angles change slightly, but it's still a bent molecule. All right. Now, if there are three atoms around a central atom and no lone pairs, we call that trigonal planar. So BF3 or BH3 would be good examples there. So if I have three atoms around a central atom, it's called trigonal. Remember, tri is a prefix meaning three because there's three atoms around the central atom, and planar because, as you can see, it's flat. Now, if we have a lone pair on the central atom, that would be called trigonal pyramidal, or you can just call it a trigonal pyramid if you prefer. So when I add a lone pair, you notice that it repels the bonds and it kind of looks like a little pyramid. Again, trigonal because there's three bonded atoms, pyramidal because it looks like a pyramid. And finally, if I have four bonded atoms around the central atom and no lone pairs, that would be called a tetrahedral. So I'm going to remove that lone pair, add a fourth bond, and that is called a tetrahedral. Remember, tetra is a prefix meaning four. All right, so I want you to try a couple more examples. I want you to try to draw the Lewis dot structure, and then we're going to talk about what shapes those are. So pause, draw the Lewis dot structure, and try to identify the shape, and then we'll go over it. All right, so here are the Lewis dot structures, and again, it's so important that you count the valence electrons before you begin. Now, the first molecule, CS2, carbon disulfide, has two bonded atoms around the central atom and no lone pairs, so it would be linear. Now, of course, there are lone pairs around the outer atoms, but those aren't determining the shape, so we only really care about lone pairs in the central atom as far as figuring out the shape. CH4 is a tetrahedral because there's four bonded atoms around the central atom, and HCN is linear because, again, there's two bonded atoms around the central atom. All right, so there are also short videos on my YouTube channel that go over just little pieces of this, like how to draw the structures again. So practice a lot, come see me for help, and work through the homework and the classwork, and you will get it.